Okay, once we are ready with the, we're done with the properties of systems, stability, linearity, memoryless, non-memoryless, and other properties of systems. Um, let's move on to some of the most important operations for signals, and when that signals are represented by functions. One of them is the convolution. The convolution is a special form or application for the inverse Laplace transform. And the convolution applies only to linear time invariant systems. So let me note that here. This is applicable only for linear time invariant systems. Okay, so if our systems is not or are not linear or not time invariant, then the convolution will not be applicable. And then we need to apply other transformations to get or to transform a system that is not linear or time invariant to one that really is. Uh, and now we can calculate or apply the convolution principle. As you remember, maybe a couple of years ago or a year and a half ago, we studied the Laplace transform. And with Laplace transform, we were uh, changing the domain of a function from time to frequency. If you remember, we do a lot of work. We did a lot of work with function f of t, x of t, and x of t, and we transformed that to 1 over s, 1 over s minus a, and all of them part of the s domain. So this is the time domain, and this is the frequency domain. Okay, the frequency domain. Uh, so the convolution is a special form of the application of the inverse Laplace transform. For example, let's think about this. Let y of t be the response of a system, in this case y of t, and let x of t be the input or the excitation signal for the system, which is the very front edge input, and let h of t be the impulse response of the system. So we have three variables and one are dependent of the other one. In this case, y of t is dependent of h of t and h of t depends on x of t. So we have the input for the system, and then according to the nature of that input, we will have some kind of impulse response, and then the impulse response of the system will become the general response or the output of that system. So the idea here is if we want to know in the time domain what is the overlap between or the interaction between x of t and h of t, then is there that we are going to apply the convolution uh, in this case, convolution integral. Therefore, once we are ready and we agree with these three um, expressions, then we can write that y of t, if we apply the convolution theorem, will be equal to x of t. This asterisk here means the convolution notation. So every time that you see an asterisk between two functions and after the y of t, uh, we make clear this is the convolution operation for x of t times h of t. And this times, or the multiplication of these two functions in this particular operation, is a special type of product, which means the convolution notation. Okay. Uh, Another definition of this is that is the product of two functions on the frequency domain. So you can have a couple of functions transformed from the time domain to the frequency domain. So if you calculate the product of them, you will have something very similar to the convolution of that functions. If we don't want to convert or transform via Laplace these signals, we can summarize that the convolution operation is equal to the integral, in this case from 0 to t, or whatever the region of integration is, the integral for this region of integration of x of tau times h of t minus tau times the differential of tau. And that is equal to the convolution of x of t, h of t. If you have these functions already transformed via Laplace to the frequency domain, then you will end up with x of s times h of s, and the product of these two frequency domain functions is equal to y of s. So these three expressions is it means the same. Okay. Let's do an example. In this case, let's do a graphical example of this, and let's start to work. Please be aware of the sequence that we are going to follow in order to execute the convolution between two functions. Let's suppose that we have two functions here. This guy is x of t is a function which equals 1 in this amplitude, and this function, it goes from -1 to 1 in the time domain. This is a kind of rectangular square impulse. This is the x of t. This is the input of the system, and the impulse response of the system is, in this case, h of t. And let's suppose that h of t has the same height, which is the value of 1, but it is going from -1 to +3 in the time domain. So this is x of t, and this is h of t. Once we are clear with this, let's do the first step. To understand the convolution, the first step, as I wrote here, is to sketch x of tau. So let's do the first step, which is represent x of tau. So we are going to take this x of t, and simply we are going to change or switch this t domain to the dummy variable tau. So this is the first step. Let's write here a little one in a circle. So this is now x of tau. The values for the tau domain, it remains the same from -1 to 1. So now we have x of tau. Now the second step, let me indicate here that this is the second step. The second step is to sketch h of tau. Okay, so in this case, we are not going to change anything but the x-axis domain. So we're going to keep the function in the same shape, the same values for the x-axis and the y-axis, but now we are going to change the t. We are going to replace the t with this tau. So we have now x of tau and h of tau. Okay, that is the second step. The third step is to sketch h of minus tau. And how can we do that? Well, let's take this function h of tau and let's flip it. It is the same if you fold this function or if you have some kind of uh, mirror operation to it. So if you see here, this is the folded h of tau. If you can see the difference, we in here the original function we are going from -1 to 3, and if you fold or flip this function, you will end up with this uh, a -3 to +1. So we are folding or flipping this h of tau. We are converting it to h of minus tau. So that's the third step. Please don't forget to do this step, because if we don't flip or fold the function, we will end up with wrong results. So first step is to sketch the function in the tau domain, the second function in the tau domain, then the second function we are going to fold or flip it to the h minus tau, so we need to invert this function. Once we are ready with this, as a fourth step, let's sketch the h of t minus tau. Okay, in this case, when we have the h of minus tau, we can end up with a general expression, which is only -3 plus tau or 1 plus tau. In this case, I am plotting an example here, which is h of t minus tau, assigning a value of t of -5. So the variable will be the t value. Tau is only the reference. This is the reference value for the original function, and we are going to switch this h of t minus tau to the left or to the right according to the t value. For example, if we calculate the h of t minus tau with t equals -5, then that's an easy one. So -3, in this case, -5 is -8, okay? And 1 minus 5 is -4. So in this case, we are shifting to the left the function uh, times the t value is indicating here. So this is the original function, h of minus tau, but when tau equals, in this case, -5, h of t minus tau is only the result of applying this displacement either to the left or to the right according to the sign of this value of t. And the x of tau, I'm sorry, it will remain the same in this case. The only function that we are going to shift or translate according to the t domain value is only the h of t minus tau. So please don't forget, first we are going to sketch the x of tau. Second, we are going to sketch h of tau. Then we are going to fold the h of tau to h of minus tau. And then we can move or represent the function h of t minus tau depending on the value of tau. Okay, so at this moment or this time, we can clearly see what the principle in an intuitive way the convolution is. So the convolution is the product, in this case, of the overlap. So if we have this x of tau in the same graph as this one, let's say this is from -1, so we will have here this -1 plus 1, -1 plus 1, and this is x of tau. Because this -4 is less than 1, so this edge is not touching or neither over any part of this x of tau. So the overlap between these two functions is equal to 0. So the convolution of these two functions when t equals -5 is 0, because the convolution is the integral of the area of these two functions when they overlap. Let me write here another quick example so I can explain that to you. So let's suppose that we have this h of t minus tau, and we have this x of tau here. Okay, so this is going from -1 to 1, and let's suppose that this h of t minus tau is going from 0, let's say, to -4. That will be a kind of overlap. So the h of t minus tau is overlapping x of tau by this amount. Okay, so according to the value of t, you will shift this h of t minus tau to the left or to the right. And if we shift this enough to the right so we can have the overlap between these two functions, the product of this will be the convolution. Okay, we are going to work a couple of examples in the following lectures. So I hope that this is clear and understandable for you. If you have any questions or comments, please let me know. I will be aware of your comments so I can support on either if you send a text message or an email, or leave your comment there in the YouTube page.